Do the treatment plants differ from the control plants? That's the question that we're going to try to answer by graphically examining our two means and taking a close look at the variability in the data behind those means using error bars. So here is a figure showing a bunch of bar graphs. Each bar graph is labeled A through E, and they all show error bars. So what sorts of information do error bars communicate? Well, error bars tell you about the spread of the data around the mean. So in the case of these bar graphs, the mean value is indicated by the height of the green bar. So for example, for bar A, the height of that bar is below the 0.6 mark, probably around 0.55. And the error bar, that is the black bar that goes above the height of the green bar and below it, is telling you about the data that goes into calculating that mean value. So a short bar means that there is a low spread in the data, and the data is clumped around that mean value. While a longer bar, like in bar C, means that the data has a larger spread and the data is more variable from the mean value. An error bar also communicates the reliability of the value of the mean. So whether or not the mean value is representative of the entire data set. A short bar means the mean is a more reliable value of the data set, and a longer bar indicates that the mean value is a less reliable summary of all of the data. So the third quality that error bars communicate is that we can actually use the error bars to estimate differences, how different the means actually are, how different the data that is represented by the means actually is from one another. So here is a table showing you some common error bars. This table lists 4 different types of common error bars. The first one is just the range, so just the spread of the extremes in the data, so like the high point and the low point. Another type of common error bar is standard deviation, so just showing the average difference between the data points and their mean. Another one is standard error. And a last one on this table is the 95% confidence interval. The last 2 types of error bars on this table, standard error and the 95% confidence interval, are the type of inferential error bars, where you can actually use these error bars to compare 2 means to see if the means are significantly different from one another. And we're going to be focused on using 95% confidence intervals to determine whether or not our means are significantly different from one another. This figure is from the Cumming et al. 2007 journal article on error bars in experimental biology. The link is down here at the bottom of the slide, and you can click on that link to go directly to the paper that this figure comes from. This figure is showing you a comparison of error bars, and the left side of the figure is for you to use when the number of fast plants in your data set for your control and your experimental treatment are between 3 and 10. So n is less than 10 or equal or less than 10 in this situation. The right side of this figure is for when n is greater than 10. And this is going to be great for your fast plant data, since the data sets that we're using all have more than 10 plants in the control group and in the experimental treatment group. If we focus just on the right side of this figure, we can see that there are two different graphs. Each graph has a C and an E on the x-axis. The C corresponds to the control, and the E corresponds to the experimental treatment. And above those, the x-axis, we can see 2 points with error bars around that point. So instead of showing the mean value based upon the height of a bar graph, we're showing the mean value with a large black dot. And the error bars, there is an arm above that black dot and a bar below it, showing the 95% confidence interval around each mean. And if we're just focused on the gold square, the right side of our figure 6, we're looking at two different instances. One instance on the left is showing us when the overlap is half of an arm. And by overlap, we're talking about comparing the control to the experimental. And we're looking at the actual arms of the error bar. And we're comparing the amount of overlap, if there is any, based upon the fraction of the average confidence error bar arm. So we're going to practice this, but here is the quick summary. If the overlap of the two arms is about half or less, then the p-value is going to be approximately 0.05. And that's typically the cutoff where we will say that that is the p-value that we need to say that the means are significantly different from one another. So if p is less than or equal to 0.05, then we can say the two means, the control mean and the experimental mean, are different from one another. If there's no overlap at all, as shown by the figure on the right side, well then the p-value is even lower. So p is around 0.01, and we can say that the means are different if the p-value is that low, but we have more confidence that the means are different. So let's give this some practice by looking at more instances of 95% confidence intervals. So here's our figure of error bars around means depicted by bar graphs on the left, and we've kept the sort of guide from the earlier figure on the right. So we've got a couple of comparisons that we can make here so that we can practice calculating the degree of overlap between error bars. So let's start with looking at the error bars for bar graphs A and B and to see if there is any overlap and determine whether or not these means are significantly different from one another. So if we take a look at the error bar for A and the error bar for B, we can sort of imagine lines going across to the two error bars, and we can pretty conclusively see that there is no overlap between these arms. And if there's no overlap, then we can say at the p is approximately 0.01 level that these means are significantly different from one another. So zero overlap means significantly different. Now let's take a look at the error bar for the A and the error bar for C. And I'll pause a moment for you to try to calculate that. All right, let's do that together. So the overlap, if you draw an imaginary line over to the A arm, we can see that about something more than a half is overlapping for this arm. And then if we consider the opposite, about a half an arm of overlap for the C arm. And so we're going to have to be a little bit more precise. Let's say 3/4 overlap of the A arm. So then if we average 3/4 of an arm and half of an arm of overlap, that's going to be more than half of an arm of overlap between these two error bars. And so we can say that they're not significantly different, despite the great difference in the height of these bars. The actual means aren't significantly different because there is so much overlap between the two error bars. All right, let's practice for C and D. So we're looking at the error bar for C and the error bar for D, and we're just going to try to determine the overlap for each arm. And so if you look at this arm for C and you look over at D, well, the entire arm is overlapping the error bar for D. So that would be one arm of overlap for C. And if you look at D, there's definitely more than one arm of overlap for D. So we can tell that the average of the overlap for both C and D is going to be well above one arm. And so that we can tell that this is not going to be significantly different, even though we see that the means have different values. The different values do not, they're not significantly different from each other due to the overlap, the significant overlap between these two error bars. And then if we do the D and E comparison, so we're going to look at the overlap for D. So what would you say if we look at the overlap for D? It's about 3/4 of the arm that is overlapping with the error bar for E. And if we look at an arm of E, it's overlapping, the entire arm is overlapping with the D error bar. So we can say that if you average greater than one bar of overlap with half a bar of overlap, or 3/4 of a bar of overlap, that's going to be greater than a half as well. And so we can say that these are not significantly different either. There's too much overlap between these two error bars. And so you'll be able to use your graph that you generate and the error bars that you place on your graph to determine whether or not your means are significantly different between the control treatment and the experimental treatment.